Hello, everyone. Welcome to my group theory lecture. In this lecture, we study functions. So, what is a function? First, let's let x and y be two non-empty sets. Then the Cartesian product x cross y of x and y is defined as the following set. So this Cartesian product is the collection of the ordered pairs x, y, such that x is in the first set x and y is in the second set big Y. Okay, so a subset little f of this Cartesian product of x and y is called a graph from x to y. A graph f is called a function from x to y. We write in this case what this as a more familiar, right? Notation, right? F function from x to y. Using this arrow notation. If whenever the two ordered pairs xy1, xy2, all right, belong to the graph f y1 equals y2. And if f is a function, the ordered pair xy belongs to f, we also write y equals f of x. So this is also the familiar notation, right? Now we talk about the two particular types of functions that are very important. A function f from x to y is said to be one-to-one or injective if whenever the ordered pairs x1y and x2y belong to the function graph, right? X1 f, then x1 must be equal to x2. This is equivalent to saying if f of x1 equals f of x2, implies x1 equals x2. Probably you are more familiar with the second statement, right? A function f from x to y is said to be onto or surjective if for every y in the set y. Okay. There's typo. There exists x in x such that the ordered pair xy belongs to f. Okay, so you can replace this by there exists x in x such that y equals f of x. Same thing. And a function f from x to y is said to be one-to-one and onto, or bijective if it is both one-to-one and onto, obviously, or both injective and surjective. In that case, it is called right one-to-one and onto, or bijective. As a noun, also, it is also called a one-to-one correspondence. Okay, a one-to-one correspondence as a noun. All right, so here comes the composite functions. I know, that you are already familiar with the composite functions, right? Okay. Uh, the so here let f be a function from x to y and g be a function from y to z. Well, in that case, the composite function or composition or functional composition, you know, so we denote it by this notation here, right? Okay, that is going to be a function from x to z. Okay, so we are combining these two functions, right? Okay, and this produces this composition produces a function going from directly from x to z. In that case, this is right. So what you see, G circle F, this is red F followed by G. Okay, F followed by G. Makes sense, right? So this F followed by G, this composition is defined by G of f of x. Okay, I forgot to close it. Parenthesis here. Okay, so gotta fix that later. Anyway, so G of f of x for all x in x, big X. The function composition, right, the circle may be considered as an operation, and in fact, it is associative, okay, associative operation. Okay, so here's a dilemma. All right, so we actually have it, the four lemmas put together. Right. So first lemma, if h is a function from x to y, g is a function from y to z, and f is a function from z to w, then we have associative law holds, like I just mentioned, right? And in this case, the composite function. So basically, like just like numbers, the number operation, right? Number operations, this associative law tells us what we mean by. So by the definition of a composite function, right? We perfectly understand what f followed by g means, okay? But what do we mean by like something like the what is that? The h followed by g followed by f, okay? Right? One may say this is my definition of that, or one might say this one, second one, is my definition of h followed by g followed by f. So, the right, okay, so people might see that as the first one, people might see that as second one. But for us, worry-free, no confusion, it doesn't matter whichever you take because they happen to be the same, right? So let's first talk about this. Actually, the proofs of all these four lemmas are pretty much straightforward, okay, from the definition. Uh, so let me get to my notepad. Okay, so lemma, we have three functions, right? So here we have h from x to y, and G from Y to Z and F from Z to W, right? We have three functions here. So it involves four sets, right? So let me first draw like a little picture. So this involves four sets, okay? So I'm gonna represent each set by a circle, a circled set, right? So let's call this X, this guy Y, Z, W. And we have H, we have G here, and we have F here, right? Okay, so you know that there are two different ways we can, combine these three maps, right? So first way we can do is, first combine these two functions, right? Okay, so combining these two functions from x to z, right? From x to z, so there will be, h followed by g, right? That will be right h followed by g, and then I'm going to combine these. This is h followed by g and f, right? So together, right? I will get h followed by g followed by f. So that's one way we can combine. Another way we can combine is following. So this time I'm going to combine actually these two first. Okay, these two first. Oh, actually, I wish I left some space here. So, right. So if we combine these two first, it'll be, the G followed by G followed by F. And then we can combine, the HN, the G followed by F. So together from here to here, right? Okay. So that would be, the H followed by G followed by F. This mapping. So what this lemma says is, either way, these are going to be the same. Okay, let's prove that. So here's the proof. Okay, so by definition, so let's start with this guy here. So, the H, so we do this first. So H followed by G and then followed by F. So when it acts on, an element in this first domain X, right? Okay. By definition, that is going to be F of H followed by G of x. So that equals uh, now here inside the parentheses, right? That's going to be the g of h of x. Again, by definition of a composite function. Now this can be written as, g followed by f of h of x. And that equals, again, by definition of composite function, g followed by f, right? Okay, so h followed by this guy here, g followed by f, acting on x. So here, like a choice of x was arbitrary, and for any x, these two guys have the same functional value. So therefore, uh, that equals this guy here. Okay, so this completes the proof, right? So like I said, it's a straightforward. Okay, so now let's move to next lemma. If both f from x to y, a function f from x to y, and another function g from y to z are 1 to 1, so is the composite function f followed by g, which is going from x to z. Again, its proof is pretty much straightforward, okay, by the definition. So here's lemma. So the statement is f is going from x to y, and g is going from the y to z. So both are, this guy is 1, 2, well actually there's a shorter notation for this, okay? So the 1 to 1, we also use this notation, 1 to 1. So this guy is also 1 to 1, and that implies one little too far. In that case, the composite function g, f followed by g, so f followed by g, which is going from x to z. This guy is also going to be 1 to 1. Okay, so here comes the proof. So to show 1 to 1, we act right. So we start out with the f followed by g of x1 equals f followed by g of x2. Okay, start out with this. So what we want to show is, in this case, the pre-images, right? Pre-images, x1 and x2 have to be the same, right? That's what we want to show. So this implies, by definition, g left-hand side is g of f of x1. That equals, so right-hand side again by definition, g of f of x2. Okay? Now this implies f of x1. So those two pre-images, f of x1 and f of x2 of g, right, have to be the same. Why? Because of the condition. This condition here, g is 1 to 1. Since g is 1 to 1. Okay? Now this implies that you know where the rest of the story goes, right? So since these two are the same and f is 1 to 1, the pre-images x1 and x2 have to be the same. Okay? Since f is 1 to 1. Okay, so this completes the proof, right? This completes the proof. So what that means is, f followed by g is a one-to-one function, right? Easy. Okay, so third one, if both f and g, right, same functions, right, are onto, so is, the f followed by g, that is going to be also onto. So this implies that the composite function f followed by g that is going to be also onto. Okay? Proof. So to show that f followed by g is onto, we pick an arbitrary element in this set Z. It is called codomain. Okay, codomain. So we pick arbitrary element Z, little z, little z in big Z. And what we want to show is that there exists an x in the domain, right, which corresponds to this little z. So in that case, we call it, call the function onto, right, onto or surjective. Okay, right. So in this case, since G is onto, G is onto uh, there exists an element in y. Okay, so I'm gonna use a little y. By the way, in case I'm sure that you have seen this notation somewhere, but if you are not familiar with this, this is like what? It looks like a flipped E notation, right? That's a logical symbol. Okay, that's this guy is a logical symbol. It is flipped E, and what it means is there, okay, exists. I thought, we use this along with other like logical symbols a lot when we do mathematics, because we want to make our statement, not too verbose, like too wordy. Okay, so we try to make it like concise, more short, using like a simple, the symbols and the logic. It's particularly logical symbols. Actually, this implies notation. This is also logical symbol too. Okay, but I try not to use them much because I figured some of you uh, may not be familiar with those, but right now I want to introduce one. So this is a flipped E notation, means there exists. Okay, right. So it's good to know, and it's quite convenient. Okay, when we write mathematics. Okay, so there exists Y in the domain Y, such that, okay, such that that's abbreviation for such that uh, G of Y equals Z, right? So I'm merely writing this down by the definition of onto function. Now, we also know that by the condition given, f is onto. So since f is onto, we also know that there exists, okay, there exists x in x, okay, so an element in the domain x of f such that f of x equals y. Now, let's see what happens when this f followed by g, right, acts on this x value, okay? So by definition, that's g of f of x, and that equals g of f of x equals y. So g of y and that's Z. So now let's read what we have here. We picked arbitrary element in the codomain of f followed by g, right? And what we showed is that there exists an element. Okay, you can find an x, little x, and this domain x such that which corresponds to this little z under the function f followed by g. Okay, f followed by g. So that's what it says, right? F followed by g acting on x equals c. Okay, right. So this completes the proof. Okay, this by definition this completes the proof. Oh, by the way, in case that you are wondering, so I put like what the empty square, okay, empty square, at the end of the proof. So which means, that yeah, that's what it means literally, the end of the proof. Okay. By the way, like these two, uh, I mean not these two, but this symbol like an empty square is being used in two different the meanings, right? Depends on the like mathematicians. Okay, so the I don't know. This is not important. Okay, but I might write it down. It's just good to know. So in mathematics, this could have two meanings. Okay, maybe I write that as an aside. So as an aside. The symbol has two meanings. Uh, this could mean the empty set. Okay, same as more familiar notation. Okay, uh, this is due to, if my memory serves correctly, this is due to the secretive Frenchy mathematical society called Nicolas Nicolas Bourbaki. Bourbaki. Okay, Nicolas Bourbaki. Okay, this is it. Very interesting. The group of French group of mathematicians. Yeah, I said actually society. This is it wrong. This is more of a group. Okay, group. The reason, yeah, I chose to use group instead of society. It is not a society. When you say society, when it is not necessarily true, uh, often like in certain like professional societies, the being a member is a privilege also. So not everybody can be a member easily, right? But in this case, this Nicola Bourbaki, right, is not inclusive, quite. You have to be really prestigious mathematicians, to be a member. There's so much interesting stories about, Nicola Bourbaki, so I rather not to delve into that. But, uh, those particularly, great, the French mathematicians, right? You probably, easily guess that they are members or they were members of, Nicolas Bourbaki. Okay. Initially, they started out as a French, but later on, non-French mathematicians were recruited as well. Where, that happens when there were no better, the French mathematicians in the like in certain particular, the subject of mathematics. Anyways, yeah. So this symbol is due to Nicolas Bourbaki, and also this, empty circle also could mean the end of proof. Same as maybe this might be more familiar to you, QED, where I prefer to use this, uh, this is shorter. This is due to uh, the great American mathematician Paul Harmos. Paul Harmos. So, named after him, it is called the Harmos symbol. Okay, right. So this just a little aside. Okay, so the last lemma is if both f from x to y and the function g from y to z are bijective, so is the composite function f followed by g from x to z. Okay, that's pretty much clear, right? We can get it. We can clearly obtain that by combining the lemma 2 and lemma 3. Okay, right. Moving on. Okay, so I think this is a good place to stop. So I'll stop here for the moment, and I'll continue uh, the rest of lecture. Separate. The screencast. I'll see you soon. Thank you.